So welcome everyone. I'm Fatima, and with me I have Joanna, who co-hosts this Data+WOMEN Romandie group with me. We both are enthusiasts of Tableau, but also in general, we love working with data, and we work for Arguza. Just a very quick reminder or introduction to people who are new to our group. So Data+WOMEN is a community that is aimed at promoting the work of women who work in data, not specifically Tableau, but around data topics, by giving them a platform to share their knowledge and experience. But more broadly, we love speaking to people who have come up with innovative ways of working with data. For example, Brian, as we will see just in 5 minutes. Please get in touch with us if you have questions, if you would like to be a speaker, or if you want to suggest a speaker, if you want to suggest a topic. We're always looking out for people who have new ideas around data and how to use it. We also would like to share what other stuff is going on around this ecosystem. So here are some interesting events that are coming up. We have on May 3rd, there's a Zoom webinar about data security with Tableau and Snowflake. So basically how to implement row-level security. On June 21st, on June 2nd, we have the Tableau user group, or TUG as it's called, in Geneva. So it's a physical event. And on June 21st, there is again a Zoom webinar about a product called Make Your Data. They will show you how to test your prototypes by generating fake data but relevant data using this product. So how does our event work? Well, a recording of this session is being made and will be made available, so you don't need to rush and write down notes. The links to the technical material will also be made available. Our next event, so the next Data+WOMEN event, will happen on the 27th of September. We do not have a topic or a speaker yet. It will most likely be hybrid, but we will share this with you in a follow-up email. So again, do not worry about writing down details from this event. Just to enjoy the event and ask questions in the Q&A or comments in the comment section and have fun. So with that, I will just briefly introduce Brian Moore, who is our speaker today. His work caught my eye when he published his Tableau mandala plots on Tableau Public. If you have not seen them, we will send a link in our email so you can look at them. That work is insane. He is a lot of things, but I think the most important thing is a general Tableau fanatic. So yeah, I think that without further ado, I will hand it over to Brian to start his presentation about drawing curves in Tableau, because he is somewhat a wizard in that sector.
All right. Well, thank you very much for having me. Are you able to see my screen?
Yep.
Yeah. Okay, great. Yeah, so my name is Brian Moore, and yeah, today we're going to be talking about creating curved elements in Tableau. So I'm hoping to make this presentation at least somewhat interactive. If you'd like to follow along, you can go to domorewithdata.com, click on this resources link up in the top right corner, and then this top link here, you can download the workbook and the sample data that we're going to be covering today. You won't actually need the sample data. Everything you need should be in the workbook. It's packaged with all the data sources already. So you can go ahead and download that workbook. And while you're doing that, just a little bit of background on myself. So I've been using Tableau for about 8 years now. Before that, I was an Excel power user and couldn't imagine using anything other than Excel for reporting and analytics. But my wife's company had just started using Tableau. She tried for months to convince me to learn it. I was convinced it was just a fad and didn't take the time. Eventually, she sat me down, gave me a quick demo, and I was blown away. It was love at first sight. Within just a couple of months of that, I started my first job as a Tableau developer, which was actually at my wife's company on her team, sitting right next to her. So I have her to thank for everything that came after that related to Tableau, which you'll see is a pretty common theme throughout this intro. Then a few years ago, I was working in higher education as an enrollment analyst, and I was really bored. I was pretty good at Tableau, but I wasn't learning anything new. I was even considering a career change. But then again, my wife came to the rescue. She recommended that I check out Tableau Public, start getting involved with the community. So I started attending local Tableau user groups. I started following and interacting with people on Twitter and LinkedIn. And I started building fun stuff on Tableau Public. And honestly, getting involved with the community just changed my life. So not only did I start having fun again with my job, but I've learned just an incredible amount from other people in the community. So that was a huge turning point in my career. Flash forward a few years, I'm now a senior database and analytics consultant at ClearTelligence. I'm also a member of the newest cohort of Tableau Visionaries, formerly known as Zen Masters, and Tableau Public Ambassador. I also co-lead the Boston Tableau user group. I'm a co-author of the Tableau blogging site, DoMoreWithData.com, co-leader of the community initiative, the STG Biz project, and just generally very passionate about Tableau and data visualization. Funny enough, my wife, Jackie Moore, is also a consultant at ClearTelligence, also a Tableau ambassador, also a co-leader of the Boston Tug, also a co-author of DoMoreWithData.com, and also a co-leader of the STG Biz project. So she's my partner in life and in all things data, which is pretty awesome. So yeah, I would definitely recommend giving her a follow on Twitter and Tableau Public. Her name is Jackie Moore, and she's the smartest person I know. So. All right, so let's talk about curved things in Tableau. So think about some of your favorite pieces of data art. I'm willing to bet that the majority of them contain some type of curved element, and there are a few reasons why I'm willing to bet that's true. First, there have been multiple scientific studies that have shown that when it comes to art, humans prefer curves over straight lines and corners, and data art is no different. And there's also the wow factor. So as you probably know, curves don't really exist in Tableau. They take effort to build, and most people just don't know where to start. So this can be a good starting point for you here. So we're going to walk through the technical process of building curved elements, from densifying your data all the way up to building your views. And we're going to focus on 3 types of curved elements. So we have circles, Bezier curves, and sigmoid curves. And there's a lot of really cool stuff you can do with these three things. So you can find all of the information I'm going to cover today. I believe we're going to send out the links, but there are a series of blog posts on DoMoreWithData.com called Fun with Curves in Tableau, and there's a different post for focusing on each of these types of curves. All right. So to build any type of curved element in Tableau, you need to densify your data. So you may have heard that term before, but if you're not really sure what it means, it's basically just creating additional data points. So imagine you have a data source and it has just 3 rows, but you need some additional data to be able to draw some polygons or draw some of these curved elements. You can do what's sometimes called a Cartesian join or a cross join to a densification table. So in this case, our densification table is just 1 column and 5 rows. So the result of that Cartesian join, if you were to join these 2 together, you would end up with 15 rows. So now we have 5 rows for our first row in our source data, 5 rows for our second row in our source data, and 5 rows in our third source. And now we can use these additional data points to do some drawing in Tableau. To do that cross join or Cartesian join in Tableau, just going to pick one of the data sources here. So first you would drag out your source data and then double click to go into the physical layer. Drag out your densification table. So here I have my source data, here I have my densification table, and then I'm just going to join those together with a join calculation. So on both the left side and the right side of the calculation, just using a value of 1, just to join them together. And the result will be that Cartesian, the Cartesian product. There are a few things to keep in mind when you're building your densification table and choosing how many rows to include. So if you include too many rows, you're going to really hurt the performance on your dashboard. So, think about it. If you have 10 records in your data source and you put 10 records in your densification table, now you're at 100 records. If you have 100 records in your densification table, now you're turning that 10 records into 1,000 records. So you're really blowing up your data source when you do this densification. So you want to keep that in mind when building the densification table. But on the other hand, if you have too few rows, then your curves won't end up looking very smooth. They'll be kind of choppy and jagged. So it's kind of a balancing act. But here's a quick demonstration of how the number of rows can affect the shape of a circle. So you can't draw a circle with 1 point or 2 points. If you draw one with 3 points, you get a triangle, diamond. And you see as the number of points increases, you can see the circle starts to take form, starts to get a little bit more and more round, and then you go all the way up, then you finally have a pretty nice circle. So if I'm drawing a circle of this size, I'll probably use somewhere between 50 and 100 points. If I'm drawing a small circle, maybe 20 or 30 will do. So when you're drawing a curve in Tableau, you're not actually drawing a curved line. You're drawing a series of straight lines. And the more points you have in your densification table, the shorter those lines become. All right, so now on to our first type of curved element, which is circles. So you may be wondering why you would ever need to know how to draw a circle in Tableau. Tableau already has a circle mark type, and that's a fair question. But the calculations needed to draw a circle in Tableau are the exact same calculations you would need to build any type of radial chart you can imagine. So this is more about learning the technique so you can apply it to your own custom charts, and less about actually drawing circles. Though I do use this technique pretty frequently on Tableau Public to draw circles when the exact size of the circle is important. So it's really easy to control the size based on this, with all of the options in Tableau to resize. Like sometimes the size and ratio to other things kind of loses its meaning, but with this technique, you can ensure that that each size is sized exactly how it should be based on area or whatever other metrics you're using. All right, so if you've downloaded the sample workbook, I've already built all of the data sources into the workbook, but here's a look at the sample data we're using. So the source data has 10 records that we're going to use to draw 10 individual circles. And we're going to use a densification table that has 50 points. So just one column called points with rows 1 through 50. And once you have your data source built, there are only 2 things you need to know to be able to draw a circle. The first, you need to know the distance of each point from the center of the circle, or the radius. So that's this blue line here. And you need to know the position of each point around the circle. So for our circles, we want the area of the circle to represent the value in our data source. So here we have this value column. So we want to translate that, we want to calculate the radius based on that. So the area of the circle represents that value. So to do that, to calculate the radius, we just use this calculation here, which is the square root of our value field divided by pi. Again, all of these calculations are also built into the workbook. So if you have downloaded it, you can dig into the calculations in there. Okay, so that is the first input. That gives us the length of this blue line here. The second input, the position around the circle. Imagine you're looking at a clock. So 3 o'clock would be 25% around the circle, 6 o'clock would be 50% around the circle, 9 o'clock would be 75% of the circle, and so on. So it's going to be a percentage between 0 and 100 that represents how far around the circle a point appears. And to calculate that, we just divide our points field from our densification table divided by essentially the number of records in our densification. So the max value in that densification table, which would be 50. So for our first point would be 2% around the circle. The second one would be 4%, 6%, 8%, and all the way around until you reach the 50th point, which would be at 100%. All right, so once you have those two inputs, you can just plug them into these two equations here to get the XY coordinates. Again, you can find these calculations in the workbook or on the blog posts, but these are the calculations here using our radius calculation and our position calculation. Oh, went too far. Okay, so once you have those, now we're going to build our circles. So if you're following along at home, we're going to use the circle data source. We're going to right click on our X field and drag that out to columns. The reason that I'm right clicking and dragging it out is that allows you to set the aggregation before you bring it out into your view. So if I just drag out X, it defaults to sum and then I have to go in and modify it. But if you right click and drag, then you can set that aggregation right away. Or in this case, we're going to use that field without any aggregation. So we're going to use this top option here, which is just our unique X values. And then I'm going to do the same thing with the Y field, but I'm going to bring that out onto rows. And for now, I'm just going to filter on our first circle. So if I was to bring out our points field onto label, see, these are our 50 points from our densification table, starting at 1 and wrapping around the circle until we get to 50. And if I bring out that position field that we calculated, you can see we're at 2% around the circle, 4%, 6%, all the way around. 50% is halfway around the circle, and then 100% is all the way around. All right, so now we have all of our points. Now we just need to turn these into circles, which we're going to do by changing our mark type to a polygon. We'll take our circle ID field and drag that to color. If you don't want it on color, you can bring it on to detail. It just needs to be somewhere on the view to partition the polygons. And then we're going to use our, our points field on the path. So the path is what tells Tableau what order to use to connect those dots. So if you remember, we had points 1, 2, 3, wrapping all the way around the circle. So we're going to tell Tableau we want to use those values to connect our dots. So think about like connect the dots. Here we would be drawing a circle with those 50 points. Again, I'm going to right click, drag that onto path. And there we go. So you're probably thinking two things now. One, these look like ovals and not circles. And two, we only see two of them. So the reason it looks like oval, or they look like ovals, is because here, you know, our pane is much wider than it is tall. If you were to put this on a dashboard, you know, you would want to make sure that you set the height and the width of them equally, and you might even want to fix the axes so they're the same as well, just to ensure that you have that nice uniform circle shape. All right, and the second thing, right now we're only seeing two of them. So that's because all of our circles currently have the same starting point. So they're all starting at 0, 0 in the center, and then we're kind of building the circle around that. So if I was to click through these, you'll see we actually do have 10 circles. They're just currently stacked on top of each other. So we could take our circle ID field here, drag it out onto rows, and we can see our 10 circles. We could drag it out in columns and see them there. What I like to do is I like to have everything on the same pane. So rather than having these 10 distinct panes, I like to have them on the same pane, and you get kind of complete control over how you can how you position them. So I like to use what we'll call an offset value. So I'm going to use this parameter up here of circle spacing. Right now it just has a value of 10. And I'm going to create a calculated field called circle offset. And that is just our circle ID times this parameter. So the value for our first circle will be 10. The value for our second circle will be 20, 30, 40, and so on. All right, so now if we look at our X calculation and we add that offset value, now we have 10 circles on the same plane. If we take our Y calculation and add it there instead, now we have 10 circles in a single column, but all in the same pane. And the way this works is basically it's moving every one of our points an equal amount, either up or down, depending on whether you're doing it to your Y or X value. But the way that I like to think about it is rather than moving every point, I think about it as like creating a new starting point for each circle and then building the circle around that. So instead of our first circle starting at 0, 0, it would be starting at 10, 0. Our second one would be starting at 20, 0. It's essentially the same thing, but thinking about it that way makes it a little bit easier when you get into some more complicated examples, which we're going to do in just a moment. Yeah, so if you calculate those offset values, if you add them to X, you get a row. If you add them to Y, you get a column. If you add them to X and Y, you end up with a diagonal line. All right, so those are some easy ways to plot your circles in a line, but we're talking about circles here. So we're going to try to plot our circles in a circle. So to plot these around a circle, we need to figure out what values to add to our X and Y coordinates. So we need to find our new starting point for each one of our circles. We have 10 circles and we want to plot those around a circle. We can use the same exact calculations we used before to find the new starting point for each of those circles. So once again, we just need two inputs, the distance from the center of the circle or the radius and the position of each point around the circle. In this case, the radius can be a constant, it's not representing any value, and we want it to be the same for every point. So for that, we're going to use a parameter. So I have a parameter just called base radius. And for the position around the circle, so previously to draw our circles, we had to plot 50 points around the circle. Now we just want to plot 10 points around the circle, one for each of our individual circles. So the calculation for that would be the circle ID field divided by the maximum circle ID field. So we have 10 circles. So the first circle is going to appear 10% around. The second one will be 20%, 30%, 40%, all the way around to the 10th circle at 100%. If we plug those two values into the same X and Y calculations that we used before, but here we're going to call them base X and base Y. But same exact calculations, you plug in the radius and the position to get the X and Y values. And then all we have to do is add those to our X and Y coordinates. So to our X values, we're going to add base X. And to our Y value, we are going to add base Y. There you have it. Now you have 10 circles drawn in a circle, and you can change this radius, which will change how big that inner circle is. You may not be able to see that the circle is changing because these aren't fixed, but they will appear larger. All right. All right. So the key takeaway from that section is, to build any kind of radial chart, anything you can imagine, you just need those two inputs. The difficulty for calculating those inputs will be different depending on what you're trying to do, but the inputs will always be the same. And it's the distance from the center of the circle and the position around the circle. All right, so now on to our second type of curved element, Bezier curves. And remember, if you don't catch everything today, you can learn a lot more about all of these techniques through the blog posts on Do More with Data. All right, so there are a lot of different types of Bezier curves, and they can really vary in complexity. But today we're going to focus on quadratic Bezier curves, which have 3 control points. An easy way to think about the control points is that there is a starting point, a midpoint, and an end point, and these 3 points create a triangle. So the starting point and the end point are simply just the start and end of your line. The third point, the midpoint, is going to determine the shape of your curved line. So all 4 of these examples here, they all have the same start and end point, but the varying midpoints create very different curves. So in most applications in Tableau, we're going to be dealing with curves like we see in example 1 and example 4. So here the midpoint is exactly halfway between the start point and the end point, creating an isosceles triangle. For this presentation, we're going to focus only on example 1, which is an equilateral triangle, meaning all 3 sides are the same length. So again, if you've downloaded the workbook, I've already built out all of the data sources, but here's a look at the data we'll be using. So we have 10 rows of data that we'll use to draw 10 curved lines. We have starting and ending points for X, and we're going to use 0 for all of our Y coordinates. So all of these lines will be on kind of a flat plane. And so they'll start and end on the 0 axis, or at 0 on the Y-axis. And for our densification, we're going to use the same table that we did in the previous example. So just 1 column named points with 50 rows, values 1 through 50. All right, so now for the inputs. So as I mentioned before, we're building Bezier curves that have 3 control points. So our data source has 2 of the 3 points that we need. We have the coordinates for our starting points and the coordinates for our ending points. So if we look at our data, see line 1 is going to start at 1, 0 and end at 10, 0. Line 2 is going to start at 3, 0 and end at 15, 0. Line 3 at 4, 0, end at 7, 0, and so on. So we just need to calculate the coordinates for that, that third set of points. So in the example up here, since we're using equilateral triangles, we can calculate these values here pretty easily. In this example here, first we want to calculate our X value. So this triangle here is going to start at 0, 0. It's going to end at 10, 0. So the X value of our midpoint is just going to be exactly halfway between those. So halfway between 0 and 10, our midpoint is going to be 5. So to calculate this in all of your rows and data, to build this as a calculation, just take your X start value plus your XN value and divide by 2. And that'll give you the first coordinate for this third set here. For Y, we need to calculate the height of this triangle. So we know because this is an equilateral triangle, all the sides are going to be the same length. So we can calculate the length of any side by taking, so we'll use this side because that's the easiest one. So we'll take our 10 minus 0. We know the length of this side is 10. So that means the length of all of these sides is 10. And to calculate the height of this triangle, we just plug that 10 into this calculation, which will give us the height of the triangle, which is 8.67. So to calculate that for all of your rows, you just take your xn minus your x start to get the length of your triangle, and then multiply that by the square root of 3 divided by 2 will give you the height of the triangle. All right, so if you use both of these calculations, we now have 3 sets of coordinates for all 10 of our lines. So if we were to stop here and plot those points, we would have 10 equilateral triangles of different sizes and starting at different points along the x-axis. So now to turn these triangles into curved lines. So we just need a couple more calculations. So we've already done these ones. The next calculation we need is t. Think of t as similar to the position calculation in the circles example. It's going to be a percentage value that's used to evenly space points along our line. Really, the only difference here between t and that position calculation is that t has to start at 0 and it has to end at 100%. So if you remember at the circles, the first point was at 2, the second one was at 4, and then reached to 100. So we just have to modify that calculation a little bit to make sure that it starts at 0, ends at 100%, and then is evenly spaced between those. So to do that, we just subtract 1 from our numerator and the denominator. All right, and once we have our 3 sets of points, we have t, then we can just plug in those 3 inputs into our x and y coordinate, or x and y calculations for the Bezier curves. You can see that these calculations are exactly the same, except the calculation for x uses our 3 x values, and the calculation for y uses the 3 y values. All right, so now let's build the curves. So if you're following along at home, just click on the Bezier demo tab, and then we're going to use the Bezier data source. So I'm going to right click on X, bring that onto columns. We choose it without aggregation. I'm going to do the same thing with Y. I'm going to change the mark type to line. And we'll take our line ID and bring that onto color. So anytime you're working with lines or polygons in Tableau, it may work without putting anything on the path field, but I always recommend addressing the path, because as this gets more complicated and you add more fields, things might start breaking and you don't know why. So just addressing the path at the start can help with that. So I'm going to take my points field and I'm going to drag that to path. It's not actually going to change the view. It's just kind of a good practice. So here we have it. Now we have our 10 curved lines. You could also, if you wanted to, you could change those to polygons and you create these nice little rolling hills. There you have it. That's how you draw a Bezier curve. So that's a relatively simple example, but now let's take what we learned here and what we learned in the first section and combine them, and the result should look pretty familiar. All right, so first we're going to plot our x values in a circle instead of on a straight line. We know that from the first section that in order to plot them around the circle, we need 2 inputs. We need the radius and the position around the circle. So for the radius, we want all of our points to be equally distanced from the center, so we can use that base radius parameter again that we did in the first example. The calculation for the position is a little bit trickier. So we need to know the maximum x value, but we have 2 x columns. We have an x start and an x end column. If we assume that all of the lines are moving from the left to the right, you can assume that x end is always going to be higher than the x start value. And you could just take the maximum value from that, but let's not assume anything. And we're just going to use a LOD expression to get the maximum value of both columns. So that's this calculation here called max point. And the way this works is basically this section here, from here to the right, is going to get the maximum value of those 2 columns for each individual row. And then we're wrapping that in a fixed level of detail calculation to get the maximum for all rows. So this will give you the maximum value from either of those 2 columns. So if we look at our data, the first part of that calculation will take the max of this versus this versus this, and then the second part of the calculation takes the maximum result of all of those results. So the maximum value of either of these columns would be 15. All right, so now we need to plot both our starting points and our ending points around the circle. So we need to calculate the position for both. So to get the position for the starting points, very similar to what we did in the first example, we're just going to take our x start value and divide it by that max point, and that'll give us that position around the circle where each of our lines will start. Then we'll do the same thing for the end of our lines, and that's going to be just our xn value divided by that same max point, and that'll give us the position around the circle where our line is going to end. So if we take a quick step back, we know we need 3 sets of coordinates to draw our curved lines. We need the coordinates for the start of the line, the coordinates for the end of the line, and the coordinates for the midpoint. Lucky for us, since we are dealing with a circle has a very convenient midpoint, which is just 0, 0. So we're going to use 0, 0 as our midpoint, and then we just need to calculate the coordinates for the start and the end, which we can do with the same calculations we used before. So first, we're going to calculate the coordinates for the start of our line. That's this circle x start and circle xy. Same calculations we used before for the circles. We're going to use the base radius for the distance in the center, and then we'll use our position start value. So that will give us the coordinates for the start of the line. We have the coordinates for the middle of the line, which is going to be 0, 0. And then for the end of the line, it's these same calculations, but using the position end field instead of position start. And if we plug all of that into our Bezier curve calculations, so here's the start, our zeros, and the end. Now, if I take those circle x fields and drag them out instead of the standard x and y, and there we go. So now we are drawing our curves around a circle, and here is really the foundation of a chord chart. So if you've ever used a chord chart, this is how they're built. All right, so yeah, so this chord chart here uses the same exact calculations as the first example we did with the Bezier curves. We just used a little bit of additional math to calculate the coordinates for the start and the end points. So for example, line 2 in our data source was going from 3 to 15. So if you look at this, our line was going from 3 to 15, but it was on a flat y-axis. All we did is we took this axis and we wrapped it around a circle. We are still going to 3 to 15, except instead of this being on a flat line, we created a circle with it. But that's how you create a chord chart. So the same exact calculations. Yeah, really, you can calculate the coordinates for those 3 sets of points in a lot of different ways. It really depends on your use case. But once you have them, it's just a matter of plugging them into those x and y calculations, and you'll get you those curved lines. All right, so now on to our last type of curve. We'll go through this one pretty quickly. So sigmoid curves. So whether you know it or not, these types of curves are everywhere on Tableau Public. So Sankey diagrams, curvy bump charts, dendrograms, curved lines on a map, all these different types of charts all use the same type of curve, and they're all created in very similar ways. So we're going to cover a couple of quick examples, but the same technique can be applied to really like an endless number of custom chart types. So there are 2 different models that you can use to draw sigmoid curves. We'll call them the standard model and the dynamic model. Today we're going to focus on just the standard model. So think about most types of charts that use sigmoid curves, that they have something in common. The start of all the lines and the end of all the lines are uniform. So, you know, if your chart is going from left to right, all of the lines start in the same column and they all end in the same column. When both of these are true, when they have a uniform start and end, you can use the standard model. If either of those are not true, so this mess up here that doesn't have either of those true, or this one where they both start in a uniform column but end in different columns, in those cases, you'd have to use this dynamic model, which you can learn more about the dynamic model in the blog post. so let's take a look at the data we'll be using for our first example. So we have 12 rows that we're going to use to draw 12 curved lines, and each of our lines has a starting position and an ending position. I know we've used the term position in past examples, but here think of it as more of kind of like a ranking. So position 1 is at the very bottom, position 2 is above that, 3, 4, 5, all the way up to the maximum number in your data set, which in our case is 12. You may notice that the densification table here looks a little bit different. So instead of just a single column of points, we now have 2 columns. We have T and path. The path field would be used to tell Tableau how to connect the points, similar to how we used points in the past. And the T field is going to be used to draw the curve, and it's going to be a value evenly spaced between -6 and 6. For our example, we're going to be using 25 points. So we'll have a value at every 0.5 increment. So -6, -5.5, -5, and so on. You could also use 50 points for a smoother curve and have a value at every 0.25 increment. Really, you can use however many points you want. You just have to do the math to evenly space them between -6 and 6. And why -6 and 6? I have absolutely no idea, to be honest with you. All I know is that those are the values needed for the Sigmoid calculations to function properly. All right, so to build our 2 lines, we only need 2 calculations. First is the sigmoid function, and this is just a mathematical function. The calculation will always be the same. It'll never change. And here's that calculation there. And the second one, we're going to use our starting positions and our ending positions along with sigmoid to create our calculate our curve values. So essentially what this curve calculation is doing is it's calculating the total vertical distance that has to be traveled. So this end position minus the start position, and then multiplying it by sigmoid to space the points out appropriately to get that nice S-shaped curve. We're going to build out our curves, and then we'll come back to this. Talk about it a little bit more. All right, so if you're following along at home, we're on the Sigmoid demo slope chart tab, and just click on the data source with the same name. I'm going to right click and drag T to columns. And we'll right click and drag curve to rows. I'm going to change my mark type to line. And I'm going to drag line ID onto color. Again, even though I haven't put anything on path, the view is working, but I'm going to address it anyways, and I'm going to drag my path field to path. Yeah, so there you have it, just those 2 calculations, and we built these nice curved lines. So let's take a closer look at how that works. So our sigmoid calculation is, like I said, a mathematical function with values ranging between 0 and 1, depending on the t value. So this table shows the sigmoid value for each t value in the first row. And the second row is just a table calculation that shows the difference from the previous value. So you can notice in this table at the beginning and at the end, the values don't really change much from one point to the next. But as you approach the center, the values start changing much more rapidly. And when you get to the center, at where t equals 0, the sigmoid value is 0.5, halfway between 0 and 1. If we look at this in context with our lines and curved calculation, so notice on our lines, the vertical position doesn't really change much at the beginning of the line or the end of the line, but as you approach the center, it starts changing much more rapidly. And at the very center, it's going to be exactly halfway between your starting point and your ending point. So if we just look at a quick example and plug it into our calculation, let's calculate the curve value where t equals 0. So if we look at our table here, when t equals 0, our sigmoid value is 0.5. So if we plug this into our calculation, we have our starting point is 4, plus 10 minus 4 times 0.5 is 3. 4 plus 3 equals 7. You can see when t equals 0, this is at 7. Another quick example, let's say when t equals -3. So when t equals -3, the sigmoid value is 0.047. If we plug that into our calculation, we have 4 plus 10 minus 4 times 0.047, which this part would be 0.28. So the overall value of the calculation is 4.28. And if you look at our line where t equals -3, this point is just above 4 at exactly 4.28. So that's a little bit about how that calculation works. It's a pretty simple calculation to draw a pretty advanced type of chart. All right, so in our last example, all of our lines had the same starting position, or sorry, all of our lines had different starting positions and different ending positions, creating kind of this curved slope chart. But what would happen if all of our lines had the same starting position? So for this example, I have a parameter called Sigmoid start. And I'm just going to use that in my calculation instead of the start position. So if I look at my data, instead of the start position, I'm going to use a parameter for this value. And the end position will stay the same in our calculations. So here's what that calculation looks like. And I'm going to replace curve with that field. Now we have a curved dendrogram. And what's nice about this is it's also dynamic, so you can change that starting point to kind of fit with your design. You can have it start all the way at the bottom, all the way at the end, or anywhere in between. 6.5 would be exactly in the middle. If you change that calculation so they all had different starting points with the same end point, it would be the same thing, but in reverse. So these kind of consolidation of points would happen on the right side instead of the left side. So those are a couple of things you can build with sigmoid curves, but there are a lot of others. If you look at part 3 of that blog post, I cover a few other examples, like Sankey diagrams, proportion plots, and how to use that dynamic model to draw curved lines over a map. That's all I'm going to cover today. But here are some examples of things that you can do with these techniques. You can build some really cool stuff. And I'm not saying that my stuff is really cool, but I use at least one of these techniques in nearly every one of my Tableau public visualizations. So here's the mandala that Fatima mentioned earlier. For here, I use the circle technique and the Bezier curves, sigmoid curves, circles and Bezier curves, circles and Bezier curves, circles and another type of curve, circles, circles, circles. So you can see sigmoid curves. So pretty much everything I've built in the last 2 years has used one or more of these techniques. All right, so that's all I have for you today. As I mentioned earlier, all of this information and more is available on our blog, domorewithdata.com. If you enjoyed the session or if you have any questions, please feel free to reach out to me on Twitter or LinkedIn. My information's here. Also happy to stick around and answer questions if there are any. Thank you very much for having me.
Wow, thanks a lot for sharing this. Very, very interesting and very useful to know how you actually do all the magic that that appears on Tableau Public. I have a question. With all this data prep, how big do your sources get? For for the mandala viz, for example, how big did your source get?
I'm not sure off the top of my head. Probably somewhere close to 1 million. I think.
Yeah. Wow.
But not all of those points are visible at any point. Like depending on all the parameters and filters, only certain things are visible.
Yeah. Indeed.
So probably only a couple 100,000 in the actual view itself. But.
Right. Okay. And so, yeah, I have never noticed any lag when I'm using the viz on Tableau Public. So I guess after filtering the type of mandala, you kind of have a reasonable number of lines.
Yeah, yeah, and Tableau can handle a lot of data very well. It's just if your data source already has hundreds of thousands of records and then you're densifying it on top of that, then it can start hurting performance pretty bad. But I mean, typically with Tableau Public, I'm starting with a pretty small, specific set of data and then densifying from there. So it hasn't been an issue for any of my Tableau Public work, but there have been cases where I've tried to build like a Sankey diagram at work and run into issues because you sales stable that already has millions of records.
I have one more question, but I want to ask the audience if they want to type in a question in Q&A or in the comments. No, I will let you type, and I will take the opportunity to ask so we mentioned Sankey diagrams and other cool, for example, radial charts we saw on your Tableau Public profile just now. Which one is like your favorite? Do you have a favorite one?
It's probably the manual. I had a lot of fun with that one. I really like that one.
Okay.
Yeah, that one and the Marvel universe of characters a couple months ago. That's probably my second favorite.
And in your consulting work, what kind of diagrams do you see people ask you to make?
Nothing like this, unfortunately. Yeah, I mean, pretty straightforward usually for consulting. A lot of bar charts, a lot of bands. A rare occasion we'll build a Sankey, but nothing more.
Right. Okay.
So I'll unmute, and is that okay if I ask something, because it's along the same lines?
I'll shut up.
Because sorry, I was wondering if what prompted this love for curves. It looks amazing, obviously, but as you started by saying, Tableau doesn't do curves, right? It does straight lines. So was there something that, for example, a dashboard that you're trying to build for a client that you said, this will really benefit from a Sankey or some curves, and this is what I'm going to get into?
So I got into the kind of drawing with curves because of the Tableau Public side.
Okay.
There have been a couple of instances where I would recommend a Sankey, but they are like pretty limited use cases, I would say, in a professional setting for a Sankey diagram. But really it was Tableau Public and seeing some of the really cool stuff other people have built. I don't know if you're familiar with Ken and Kevin Flerledge, who've done all kinds of cool stuff. It was really seeing their work and seeing one of their sessions at, I think it was TC19, where like they basically said, Tableau is just a scatter plot. If you can do the math, you can draw anything you want, and that like just kind of
clicked it for you. Nice. Okay, thank you.
All right. Any other questions or comments, Joanna?
No, that's it from my side. I will thank Brian, because this was amazing, and thank you for making this public and just following along. I was so mesmerized. Yeah. And it's really nice to have the template. It's a lot of fun too. So thank you. Yeah.
All right, then thanks again, Brian. We are right on time. We will share your blog post and all the links to contact you with the audience later in an email, and we also put it on our website so people can bug you.
All right, sounds great. Bug me anytime.
Bye-bye. Thanks, everyone.
Bye.
Thank you. Bye.